The punchline with the previous lecture was that pose, meaning position and heading, is central in a lot of different situations. And we made the claim that other pose-based models, like cars or underwater gliders or other kinds of autonomous vehicles, can be made to look like a unicycle. Today, I want to make this observation precise and concrete by looking at car-like robots. So here, for instance, is a picture of our autonomous car out of Georgia Tech. And the question is, how do we make this thing look like a unicycle? Well, the first thing we need is a model. And the standard car kinematics is to add another state to the system, which is the steering angle. So here is the picture that we have in mind. The rear wheels are just pointing in whatever direction the car is going, or the car is facing, which is the orientation, phi. The position of the car, well, we're going to take this point, which is in the middle, in between the front wheels, and this distance here is going to be L. So the rear wheels are L away from the front wheels. And then we have this angle, which we're going to call psi. So what we're actually going to end up doing is moving the car in this direction, and the direction then is psi plus phi. So if we make this observation into a model, we first see that the states are x, y, phi, and psi, steering angle. The inputs now that we're going to have are, as before, the speed, how quickly is the car going, and how fast are we turning the steering wheel. I'm going to call this sigma, angular steering velocity, or steering angle velocity. The model then becomes, well, x dot and v dot is, as before, v cosine, and then the direction we're going in, but the direction we're going in is now psi plus phi. Then we have an equation that relates the steering angle and the velocity to the heading of the car, and then the last component is that we can immediately influence the velocity of the steering angle. So how quickly are we turning the wheel? Okay, good. Now, what we're going to do is pick sigma and v in a clever enough way to make this thing become a unicycle. Let's start then with the unicycle itself. So this is our car model. Well, let's start with the unicycle model and do something called curvature control. So what this means is that if I want to drive along a particular circular arc, let's say that the radius of the arc is rho, and here's the car, it's going, or sorry, the unicycle, it's going, right? This is the direction in which it's going, so the orientation in the unicycle, this angle is just phi. Well, here's alpha, and simple geometry tells me that alpha is phi minus pi over 2. Okay. If I'm describing how this thing is evolving along a circular arc, then I get, for instance, that the x position is simply, let's say that the center of the circle is x naught, y naught. Then x is simply x naught plus rho cosine alpha. But because alpha is phi minus pi over 2, I can write this as x dot plus rho sine alpha, thanks to one of my favorite trigonometric identities. Well, if I take the derivative of this with respect to time, I get that, well, this thing, the derivative of that is 0. The time derivative of this, phi dot, is equal to omega. So my x dot becomes omega rho cosine phi. But wait a second, I know what x dot is. It's v cosine phi because it's a unicycle. So now these two expressions have to be the same, which means that the radius of the circle is v over omega. Now a lot of times we care about what's called curvature, and curvature is 1 over the radius. So the curvature is simply 1 over rho, which means that the curvature I would get if I have omega and v, well, it's omega over v. So the bigger the omega is, the tighter the circle, meaning the higher the curvature. If omega is 0, I'm going in a straight line, and the curvature is 0. So this is the curvature of a unicycle. Okay, let's figure out what the curvature is when we have a car. The only difference now is that the car is actually pointing in this direction, but it's going in this direction because of the fact that we have a steering angle. So as before, alpha, this angle, where we want to say where the car is, well, it's phi plus psi minus pi over 2. So doing exactly what we did before, x is x naught plus rho, where rho is the radius of the circle, sine phi plus psi. Taking the derivative, we get x dot is rho phi dot plus psi dot cosine phi plus psi. Now, let's assume that we're driving on a circle. This means that we're going to hold the steering wheel fixed, which means that this term is going to be equal to 0, because we're not changing the steering angle. Right? So we know that psi dot is 0. Well, we also have the equation for phi dot. It looks like v over L sine phi. Sorry, psi, v over L sine psi. And we also know that x dot should be equal to this expression. So what do? Well, we simply now line up v here and rho phi dot there to get the curvature. Sorry, to get the radius of the circle. So this becomes L divided by sine psi. And now we invert this to get the curvature. So the curvature becomes sine psi over L, where psi is this fixed steering angle we're driving at. Okay, then we have curvature for the unicycle, this thing. Curvature for the car, that thing. Well, we just put them equal, right? Why not? If we put them equal, then we immediately get that sine psi should be equal to omega L over V. So this is the steering angle. If I have a unicycle that's driving at omega and V, then this is what the steering angle should be to get the same behavior out. Which also means that my psi then should be arc sinus of, well, omega L over V. Well, I can't set psi directly, so what I need to do is say that this is my desired steering angle. And then I somehow need to make my actual steering angle become close to my desired steering angle. That's the name of the game here. Right? So omega d is arc sin, or arc sine, psi d is arc sinus of omega L over V. Okay. Now, arc sin is a little bit of an annoying thing to have to do. So instead, we're not going to do that. So let's say that I have this thing, and I would like d to be close to it. Well, one thing I can do is a simple p regulator, which is something we've seen. But this thing involves this arc sine, and one thing to note is what happens if we actually keep sinus in there? Well, we would get something kind of cleaner, right? So let's get rid of this and simply say that instead of psi here, I'm going to do sine psi. And instead of omega d then, I'm going to do sine omega d. So I keep saying omega, I mean psi. Sine psi d, which we know is omega L over V, which goes in there, right? So we keep the sinuses in there instead of taking arc sine. And the reason for that is that for small enough angles, this is roughly equal to the angle itself. So sinus is not a bad thing to do. Well, let's see if this works. So over on the left here, you see the unicycle, and over on the right, you see the car. And the unicycle has some omega and V, and the car is running this sinus version of a P regulator. And as you can see, they're pretty close, which means that we can basically do the same kind of curvature control on the car as we can do on the unicycle. So the moral of the story with this is, you know what? We're planning, we're getting some direction we want to move in. Here's my direction I want to move in. Well, we know the clever trick, right? The trick gives us V and omega, which is what are the speeds and angular velocities we would like. We now also know that the curvature is omega over V. So if you give me V and omega, I can tell you what the curvature is going to look like. Well, let's use this curvature idea to make the car track the unicycle, which gives us V and sigma. And of course, this V is the same as that V, so we don't have to do anything about it. The only thing we have to do is to add what sigma should actually be. And this, ladies and gentlemen, allows us to make the car act like a unicycle simply by using this curvature idea. And this generalizes to other types of unicycle-like systems where pose, again, is really important.